We've all played with magnets at one point or another. You know that there's a north-south side to each magnet. So on these magnets, there's a dot indicating the north side. And you know that they'll stick together, usually want to stick together. However, if you flip them around, we know that the two north poles repel each other. That's kind of the fun part. The north and south poles attract each other, and the two south poles attract each other. If we were to divide these magnets, we would just get smaller and smaller magnets. I mean, in actuality, if you think about it, if I stack a bunch of magnets together, this makes one big magnet. And you already know that if you divide the stack into two, I don't just get a south pole on this side and a north pole on this side. I get two smaller magnets. So they still repel. There's still two north poles, and there's still two south poles. So let's stick together now. Put them back together. I could keep doing this. So I could divide this into two, and I still get two smaller magnets. I could keep on doing this. And eventually, I'm going to get to a small amount. In fact, I can divide this even more. And it turns out that if I were to... So if we look at this, I've got just a small number of little magnets here. So we've got a bunch of little tiny magnets that are shattered, but I don't have anywhere in this pile, no matter how hard I looked, I'm not going to find a lone south pole and a lone north pole. I just have a bunch of little tiny magnets now. So a permanent magnet is really just a bunch of little tiny shards of magnets stuck together and made to kind of all line up. Now to see this, to explore this more, we can play around with nails here. A nail we know will stick to a magnet, but usually in and of itself, it's not a magnet. So I can take these two nails and usually nothing really happens. Now, if you've played with tools at all, nails and screwdrivers, maybe at one point you found that they can become magnetized. So we can do this quite easily with an external magnet. So if I stick a magnet on this end, I've now turned this nail into a permanent magnet itself. So I can pick up another nail with it. If I were to remove, it's very weak. If I were to remove this other magnet, so here we got this. If I were to remove this magnet, then it stops becoming a permanent magnet itself. So something about the presence of that external magnet is causing this to be, so if I were to move this, this stops becoming a magnet. Why is that? All right, so what's happening here? Well, it turns out that both of these materials are what are called ferromagnetic. And what that means is, if you look on the microscopic scale at least, there's going to be neighborhoods of atoms in the material, in which case all the atoms in that neighborhood are going to be aligned. That means that their north and south poles are be aligned. If I were to break this little magnet into tinier and tinier pieces, then even at the smallest scale, if I were to divide this to the scale of an individual atom, I'll still find a little dipole magnet, a little dipole magnetic material. Iron, it turns out, is a small little magnet. We can go even smaller still. If you go within the atom, you find that each individual electron, not only being an electrical charge, it's also a little magnet. Electrons are the smallest magnets we know about in nature, and they still come in the dipole form, meaning there's kind of a north pole and there's a south pole. As far as we know, and we've looked everywhere, we have not observed an individual lone north pole, north magnetic pole, or an individual lone magnetic south pole. We call those monopoles, magnetic monopoles. Now, later on, we'll learn that the equations of electromagnetism would look especially beautiful, symmetric, if there were such a thing. And so that's driven the search for magnetic materials or magnetic monopoles. But so far, none have been observed.